Hi, folks. So this is going to be our first attempt at recording one of the lessons, just in case we need to do this later. So we're going to start off reviewing where we picked up with electrochemistry. For those of you that missed these classes, this might be useful too, or if you just want to review it. So electrochemistry, at its most basic, is the study of the relationship between chemical reactions and electricity. So we really want to think about the exchange between chemical energy and electrical energy. So can we do a chemical reaction to get some energy out of it that's going to work the device? So even there, it says the applications of electrochemistry, like a battery, just the movement of, say, lithium ions in a lithium ion battery is going to be a physical change that's going to release some energy and allow electrical processes to happen. Fuel cells, similarly, but if you haven't seen what a fuel cell actually does, we would have something like hydrogen gas going on to a surface of a membrane with, say, some platinum catalyst that's going to split the hydrogen into its electrons, which will come around through a circuit. And at the meantime, we have the hydrogen protons making its own way through, and then they'll recombine, usually with oxygen, just to make water on the other side. So as we get this figured out, it's going to be a relatively powerful, relatively clean energy source, and that's where the energy or the excitement is there. For electrometallurgy, extraction, purification, that's the idea that we can use an electrical current to drive the purification of a metal. So if we get a source that has a bunch of different metals in it, then we end up, we achieve the ability to separate out the metals that we want from the ones that we can just set aside. For example, aluminum for a long time was an extremely expensive metal just because it was difficult to extract. Now aluminum, of course, is cheap, but that's because we have cheap electrical power that we can use to drive these processes. Further one, okay, corrosion. So rusting, any rusting is an electrochemical reaction. As far as we go in the military, thinking about electrical mechanical engineering, whether you're in the Navy, the Air Force, the Army to an extent, but probably a lower extent, but especially when you're on a ship and you kind of want to keep the water out of it, or if you're on an aircraft and you can't really pull over for repairs, corrosion control becomes a very big deal. Okay, so we're going to begin with a review of the oxidation number rules, just because these become especially important now. I know we saw that at the beginning of the year, but it's worth reminding ourselves. So reminding that the oxidation number in a neutral molecule or in an ion have to add up to the charge of the ion, or 0 if it's a neutral molecule. Alkaline metal atoms, so the ones to the furthest left on your periodic table, they always get a +1. Alkaline earth atoms, so think about like the magnesiums and the calciums in the second column there, they get a +2. Halogens will almost always take a -1. Fluorine always gets a -1 just because it's the most electrochemical or electronegative, all the way up in the corner where it is. Most of the other ones will take a -1. There are some rules around that, but they came up. We can talk about them if they come up. Hydrogen tends to take a +1, but it can be a -1 depending on the other conditions. Okay, so like lithium has a lower electronegativity than hydrogen, so you would get a lithium hydride. Anything that has a hydride in the name is going to be a hydrogen with a -1 on it. Oxygen gets a -2 in just about all the cases that we're really going to care about. There are some cases, say such as hydrogen peroxide, We see an ozone there, some other cases where oxygen, it can't be a -2 if it, say an ozone is a neutral atom. You got 3 oxygens, they're all -2, it's not -6, so you know that there's going to be some changes there. Okay, and why we're going to use that is because electrochemical reactions tend to change the oxidation state of the atoms, okay? So either it's going to be oxidized, so that's the oxidation number going up, or reduced, so it's going to gain electrons and the oxidation number goes down. The only confusing element there might be talking about oxidizing agents or reducing agents. So an oxidizing agent is something that is itself reduced and oxidizes something else. A reducing agent, on the other hand, is something that is itself oxidized because it's reducing something else. So if we're thinking about something like vitamin C acting as an antioxidant, that's because it is providing a source for those oxidizing compounds in your body. So it is going to be readily itself give up its electrons. So it is going to be oxidized. So it is a reducing agent. Okay. And just as a little practice, we'll go through a couple of examples just to determine the oxidation number of each element. So starting with zinc chloride, zinc can take on a couple of different oxidation states, but the most common, and we're going to see this again and again, is 2+. So that being the case and the salt being neutral, you'd have to see a Cl2, and each one of them is going to have a -1 charge. So the whole thing sums up again to 0. If you were going to see it written out, it would just be zinc Cl2, and that's what you'd expect to see. Okay, what else we got? Sulfur trioxide. Okay, so remembering back to our, you can just look at it here and follow the rules. So we have sulfur O3. Oxygen, we've already said, is going to get 2- on each of the atoms. So that's a 6- overall. So in order to keep this thing neutral, we need the sulfur to be a +6. We can also think about it as a Lewis diagram, where we have our oxygens surrounding the sulfur. We know it's going to be neutral, so we'll just put in all the electrons. And again, sulfur can take an expanded octet. So this is a perfectly fine molecule. And if you count it all up, the oxygens again are going to be counted as taking an extra couple of electrons each. And the sulfur will have lost all of its valence electrons to those oxygens. Okay, and finally, the dichromate ion. So this is something maybe you'd have to look up to see what exactly is in it. Of course, I'm just going to give it to you. So dichromate, di for the chromium, and then O7 -2 on the whole molecule. So that means that the entire ion is going to have a -2 charge. Each of those oxygens will take a -2, so this is going to be -14 overall. We know we want to get it back up to -2, so we have to have something that's going to get us to -2. -14 plus 12 gets us there. We have the 2 chromiums, so each one is going to be +6 in the end. Okay, so that's our review for oxidation states, introduction to electrochemistry, and we'll pick it up on the next video talking about balancing redox reactions. Okay, thank you very much.